So GP Singh is the CEO of Ambient Scientific, one of the founders there, and he's been an engineer in the past, so he knows his technical stuff. And he's going to be talking to us today to explain Ambient's general purpose AI processor for micro edge applications. Take it away, GP.
All right, thank you very much. So hello everyone. I am very glad to be here presenting in this prestigious conference that's been started by Linley for a long time. I have attended these in past. This is my first time presenting. Let's go right into it. I'll just introduce the company in my first slide. We started in 2017. Our goal has been to enable AI for everyday life, for everyone, for everywhere. And that means putting AI into small devices that are starved for energy, devices that need more and more computing, but they don't get it. And that's where we we targeted our focus. We are right now 40 employees. The company was founded by me and a bunch of my friends. We were self-funded for around 1.5 years. In other words, we were starving. And then we got funded in 2018. We got Series A and then Series B right now in closing. Our board of directors includes CEO and one representative from the investor. But I do want to mention we have two independent board of directors. One is Michael Helston. He is CEO of Synaptics. Another is Chris Alexander. He is the head of sales in Renesas. The board of directors we are very fortunate to have these gentlemen because they know lay of land. They have rose through ranks from being an engineer all the way to being to guiding either the entire company or a big part of the company. So we have the right management in place. Our first product is called GPX10. Even though it has the name GP, it actually doesn't mean my name. It means general purpose AI computing. X, we put it there for context processing, but X was the term that we use. So GPX10 is our first product. It has 10 AI cores. That's how the name means. In works, we have GPX4. Again, as the name will suggest, obviously, it's a 4-core AI accelerator. And also in works is our 2000 core chip, which will go for edge servers in data centers. We already have 6 patents that been approved. We actually have been having opposite problems. Our patents are getting approved too soon. We have 35 plus in pending. We just filed 4 patents in just last week. So we have a lot more patents coming because we have really invented a lot of stuff. The first product, GPX10, is in hand. I was actually going to, let me show it to you guys. This is the product we are testing right now in lab. I don't know if you guys can see it. We are testing it in the lab and we are shipping it to customers in different areas right now for these are beta customers. Agenda today, most of the presentation will be very technical in nature. We have been doing a lot of innovations for past 3 years, and I'm going to list them one by one because that's the time we will have. We'll just go in a couple of our innovations in a little bit more details. But other than that, I'm just going to list all the features and innovations that we have done. We really have done a lot of innovations because making AI worked for very, very, very low power consumption is extremely tough problem. But we are glad to say we have solved it. This is our market. Everybody by now knows that the AI is everywhere. And we are bringing AI to everybody's life, everybody's daily life, which means going into small consumer gadgets. So we now have customers engaged pretty much in each of these areas that are listed here, whether it's always on audio or always on sensor fusion for healthcare or sports or pet care, or and then always on also industrial control, some that are more sophisticated, some that are simpler. All of them need a low power consumption. All of them seem to want to do AI. So we have a very beachhead marketplace for us, a lot of challenges for us to build a team that can support so many customers, but those are good challenges to have. As we go forward, next year onwards, we'll start building this chip, which is called GPX 2K. Again, edge servers power consumption is a huge issue, and we think our technology will be able to give us a stellar product with which we'll be able to combat or to deal with the very big, powerful competitors. Here are some features that I have listed in GPX10. This is our first product, is a single chip, fully integrated AI computer. We really wanted to make it such that this becomes an entire system on chip. In this case, we'll be able to ingest data from sensors, many sensors together, be able to manipulate them, maneuver them, mix them, and then do AI inference in less than 100 microwatt. But we have designed the chip in such a way that while it can do very efficient computing for inference and anomaly detection, when required, it can actually give you lots and lots of performance. So this can really become a single chip solution for a very, very small pendant type device to whenever you need a more performance, a larger device for embedded. So this should be able to serve the entire AI market very well for the micro edge. And power consumption, you will see in our theme, power consumption is our main focus, but without compromising either the flexibility or programmability or the performance. So in some sense, we kind of defy the common wisdom, but we have been able to achieve this. So this is now you can see it, you can test it. The representative applications are always on audio applications that you guys very well know, wake up words, phrase, talk to the device, talk to electronics without connecting to the data center. A lot of industrial and healthcare where we need sensor fusion. We have built this product in TSMC 40 nanometer, even though this is a very old technology. GPX10, even in this very old technology node, will compete with the 7 nanometer devices just fine. We should have absolutely no problem. We can do up to 8 sensor fusions simultaneously in this chip. That means you can do very complex neural networks. I forgot to mention, we support general purpose neural network, means the neural network or the algorithm is fully software defined by application. We do not limit to one or the other type of network. So what that means is this becomes a general purpose fully software defined AI computer for the edge devices. For doing the AI functions, we have 10 cores or 10 AI cores in this. And for running just non-AI applications, we have an ARM with a floating point. The power consumption that we measure while doing audio processing is less than 100 microwatt. We have respected at 80 microwatt. This includes power consumption for everything, including ingesting of sensor data, mixing all the sensor data, doing neural network inference. And in this case, we measure this with the audio samples of 20 kilo samples per second. So this is as much as as a fast sampling that you would need for pretty much most of the applications on micro edge. And we are giving you a complete solution, a complete system that can burn less than 100 microwatt of power. The AI features, as I said, we support all neural networks, algorithms. There is no limitation. We have designed this chip to do both inference and training. And we expect to be able to do on-device targeted training using this device, because we have given you the performance and resolutions that is required to do so while being very efficient, all of them. Each of these cores can actually change from being doing training to inference, and they can do it in defined by the application, so completely under software control. And each core can be doing training or inference independently. It doesn't depend on other core. That means the chip can actually be doing multitasking, where it's kind of retraining or tuning the weights while the another portion is doing inference. We have given a great feature wherein the operands, both weights and input operands, can be 4-bit, 8-bit, 16-bit, and 32-bit. And this is again software defined, fully software defined, and each core can independently choose which resolution to have, all under software control. The peak performance for this chip can be 512 giga ops, and power efficiency we talked about. Looks like I'm running late, so let me go fast. This is our release schedule. We have the first release happening right now. We are able to support neural network development using C++. By end of this year, we will be supporting TensorFlow, and by end of Q1 2021, we'll be able to support other deep learning frameworks like PyTorch or Theanos and others as well, other popular networks. Let me get a little bit more technical. GPX10 SoC architecture, as I said, this is 10 core. An ARM subsystem is for running user applications, and 10 AI cores for running AI applications. There is an always-on block which runs independently. The chip is divided logically into 3 sections, as you see here. I can't point. So there is an always-on section that works independently, does not need help of the app processor, and is able to do inference, anomaly detection, and many other functions that it does. Only when an event is detected, and that event is defined by software, it wakes up the application processor. We have done power saving. If you know of any scheme that exists in the world, we have used them. And when things fell short, we invented new. So huge amount of power saving, including power getting extremely sophisticated clocking structure, which can take the chip and each portion of the chip separately from 1 kilohertz to 100 megahertz. So you can get into turbo mode. The application can define the turbo modes of different, at different levels, and do that. There is a very special architecture we have used. This is called pretty much a data flow architecture, but we have made it asynchronous. Means handshaking between different blocks is actually done asynchronously. What it means is that each block can actually run at separate speed, and unless there is new data arriving, the next block does not really function, does not do anything. This, folks, this can be a value proposition for an entire company. And in past, there have been companies that made this data flow architecture as the entire value proposition for a company. For us, it is just a bullet point. Neural networks. If you look at a neural network, they're very simple. They are just circles connected with lines. Lines in chips are, you don't even need to build them. They're just connections. So what is the big deal? The big deal is that those circles are actually, they're can of worms. There's too many things that happens in those circles. Main bottlenecks is that the mathematics used here is matrix mathematics, and matrix mathematics is a fundamentally different type of computing that, and you pretty much all of you know this by now. You need very special kind of storage devices, storage being SRAM in these cases, because you need to disperse lots and lots of variables or lot of operands to this matrix computing. So if once you make a matrix computer very fast or very efficient, you still need to figure out how to get the data to those. And then there's a lot of data exchange between one core to other core, one block to other block. So the wires that are not really scaling, those become another problem. On the SoC level, when you go, there are some things that you cannot really shake off, like the clocking, like the leakage. These are things that you have to deal with. When we started calculating, we saw that most of the SoC, just the leakage alone will be more than 100 microwatt. That means our device SoC was not possible if we did not tackle these problems. So we invented, and we really invented, folks. We have invented each of these circles that you see here. I cannot go into too much details. I'm just going to mention it. We have done our own RISC processor. We have done a matrix compute engine that is a monolithic circuit. I'll talk about these in couple of slides. We have done very specialized SRAM designs. We're probably one of the best companies for of SRAM designers. It's able to do very low leakage. The leakage reduction is tremendous. We are able to disperse vectors of vectors to a matrix compute engine in just a single cycle. So one command, you will get multiple vectors arranged properly to go to a matrix engine. We have done a very special architecture technology that's called naturally asleep. Means all of our SRAMs are actually naturally in sleep mode. Means they're burning very less leakage, but they wake up with zero latency. That means when the architecture needs, that portions wake up and do the work and go back to sleep. This thing is so inherent and so hidden in the design that our own RTL designers don't know about it. That's how fluently it has been integrated. We have done low swing signaling technology. This helps us transfer data very efficiently. And for the SoC level, we designed our own analog to digital converter, which burns less than 5 microwatt, even when it is working at 20 kilosamples per second. Another problem that is very important to understand is that there is no way you can have clocking. You cannot have, so you have to invent a new clocking device if you want to do extremely low power, because the PLL alone otherwise will consume too much power, or you have to get the clock from somewhere else outside, where just the board, trace from the board will consume more power than the PLL. So we invented our own clocking technology to conserve power without, again, limiting performance, flexibility, or programmability. I'll talk just about a few of, just a couple of these items because of the time limitation. We call it a DIGAN, Digital Analog Matrix Compute Engine, because it's able to do this entire matrix computation, one row with many columns. This engine is able to multiply just or do the part of this matrix computation just in a single cycle. We use for 40 nanometer, these numbers are given here. You will have these slides, and I don't want to spend time. We use only CMOS transistors to do all analog computing. I forgot to mention that MAC computation we do using analog concepts, because those are just made in heaven, as they call it. You use analog, MAC computing becomes extremely flawless, effortless. But of course, analog brings other problems. So we have dealt with those problems. We are able to support 4-bit, 8-bit to 32-bit resolution, as I said earlier. To this unit, we give digital input and we get digital output. Entire analog is all hidden, again, to the extent that even our RTL designers do not have to deal with anything that has to do with analog. They give digital operands as input, and they get digital output as a result of MAC operation. A little bit more about the analog. We are using DAC ADC constructs. We multiply currents with conductance. There is great papers available in industry how that is actually done. The problem is how you make it low power and how you battle noise and process variation and temperature variation and blah, blah, blah. We have used every trick in the book. That's all I can say. And it was not sufficient to get what we needed to do, so we invented new ones. These are patents that we have delayed, unfortunately, for some of you, but they will be coming up probably in a few months where you can read it in more details. But we have battled these problems, and we are able to do this analog matrix computing without any issue. We do not do any approximation. We produce only accurate outputs, and we are able to support all those resolution. I do want to talk a little bit about this architecture. Once you have a matrix compute engine that can take a whole many vectors of operands and compute, now you need to feed this monster, because to be able to compute in one cycle, you need to be able to disperse so many operands effortlessly to this engine. Otherwise, this engine will choke. So we developed a very special architecture which is able to give all of these operands simultaneously to this engine, which then computes simultaneously. You're able to compute the outputs of these MAC results simultaneously and get the output. This is a 3D memory structure, as we call. One thing I forgot to mention, our analog MAC computing is done into a custom circuit architecture. And this entire block is actually one monolithic circuit architecture. We do not do these pieces in separate pieces. This is a big hint for experts who will be trying to reverse engineer this, but this is as much as I can reveal. At the AI core, it's our own custom risk engine using 3D SRAM, and our matrix compute engine is able to do very efficient computing. For the normalization and biasing, we use standard ALU, but for activation, again, we take help of custom circuits using mixed signal approach. We, of course, combine digital and analog to make things happen. And then the crossbars, two crossbars distribute the data between different data paths units and the different cores of the AI engine. So, and then we are able to have one clock drive all of these blocks. But as I said previously, we have used asynchronous data flow architecture to so that the data flow guides the power consumption in the entire engine. So fully custom, everything from circuit all the way to architecture to our own risk ISA instruction set. Probably you'll find some time, in other forum to discuss these technologies in details. As I had said, we don't have time to go into details of each. I'm kind of mentioning them just in bullet points. Folks, the inventions we have done, we think this will serve the semiconductor industry for a very long time to come, because we have really pushed the boundaries of power consumption and performance to the next level from where the semiconductor industry is today. And we spent a lot of time. This is a demonstration of what this type of technology can do once you have been able to compute a part of a matrix in one cycle, and you're able to disperse so many operands to that engine. A 32 by 32 matrix multiplication to produce a 32 by 32 matrix. If I was to take a single single core CPU, and assuming that it has multiply accumulate engine in that, will consume around 30 to 98,000 cycles. The same operation we can do in our engine using 128 cycles. As you can see, we have obviously invented mechanism to do analog MAC equations. Whether you do it that way or not, once you have constructed this problem, looking at the system level, going all the way to circuit. So we start from the system. We kept looking for the solutions all the way. And if those circuit components were not available, we invented them. That is how we have solved the problem, looking at a holistic problem, not one at a time. If you have dealt with power consumption, experts that have dealt with power consumption, you know that power is consumed by many components in the chip. So there is no one silver bullet that you just do this and the power consumption will become very less. It doesn't work that way. You must invent at many levels to really battle this power consumption. I'm very glad to say that we have been able to give you a product that will serve very well for small devices to pretty much all of the embedded applications for AI applications, doing both inference and training. It's a fully integrated single chip AI computer that is fully software defined for its functionality. Very extensive architecture and circuit innovations to optimize power and performance without compromising on programmability or flexibility. And we invented, again, at many levels, architecture all the way to circuits. So thank you very much. And here are our contact people for sales. Please contact Stephen. He's probably listening somewhere. And for business inquiries, please contact Satish. For general inquiries, just say info@ambientscientific.ai.